There are some claims that they had in the suit that the water that was within the spacesuit, the heat was collected in there and then it was expelled.
Yeah, makes a good story, doesn't it?
Yeah, but you never see that being expelled in any of the videos.
No.
You should see that coming out of there.
Because if you did see the water being expelled to remove the heat, anybody with a modicum of understanding of mathematics could calculate the amount of water required to remove a specific amount of heat. And there wasn't enough water being carried on the astronaut spacesuits, the PLSS, Portable Life Support System, the backpacks. There wasn't enough water being carried. Maybe enough for about 20 minutes, but not enough for 8 hours, which is what some of the astronauts spent outside. Something doesn't add up here. Just about heat. I mean, it doesn't add up about a lot of things, but the amount of heat required to be removed to keep an astronaut at a reasonable working temperature, say of about 20 centigrade, 70 Fahrenheit, the amount of heat required to be removed is quite significant. So the amount of water required to remove that heat can be calculated.
You have to account for the body heat coming off when you're in the suit as well.
Exactly. The body heat the astronaut produces, it's about 100 watts, working hard. And I'm sure they were working very hard on the lunar surface for 8 hours. So how is the heat removed?
Meanwhile, at Hamilton Standard, engineers were facing a different set of challenges. Their job, as well as supervising the contract, was to build the life support system, the backpack that provided the astronaut with oxygen and kept the spacesuit pressurized at a comfortable temperature. They called it an environmental control system. It was Earl Ball's job to design it.
Nobody had ever done this before. We were going to make effectively a little space vehicle with a suit and this environmental control system.
One of the challenges was to provide the maximum oxygen for the minimum weight. To do this, Ball used what's known as a rebreathing system.
Now, normally when you breathe, you exhale oxygen and CO2, and that is just blown away, and you waste all that oxygen that you've just exhaled.
Hamilton's system removed the carbon dioxide from the exhaled oxygen by passing it through lithium hydroxide. It meant the same oxygen could be used over and over again. It was at least 20% more efficient than a traditional aqualung. In 1963, as NASA put the Apollo spacesuit through its paces, they discovered they had a problem. Everybody had assumed that cool air pumped into the suit from the backpack would be sufficient to regulate the temperature. But as astronauts now started to use the suits, they were becoming dangerously overheated.
In October of 1963, NASA gave Hamilton a 2-week ultimatum to demonstrate a solution to the astronaut cooling problem.
The whole program is in jeopardy. There was a threat that we would lose our contract if we didn't measure up to NASA's requirements.
Unfortunately, that wasn't as easy as people expected.
Dave Jennings was charged with finding a solution in record time. He was shown designs of a British garment which used water-filled plastic tubes. Jennings set up an experiment to see how well it worked. Harlan Brosey was his test subject.
We wrapped his arms and legs in PVC tubing.
We then put a sweatsuit across my body. Then, in addition, to make sure that we didn't evaporate anything off of the sweatsuit, we put a plastic suit over me, plastic boots, plastic gloves, plastic all over, so that no water could possibly get away from the body. Including my head, I believe, was covered with a plastic bonnet.
The idea was to ensure that none of Brosey's body heat could escape. Then the PVC tubes were hooked up to a bucket of iced water.
Well, when they turned on the cooling, it was just like jumping into Lake Superior. Man alive, was that cold. And then the treadmill wasn't running yet. I said, turn on the treadmill. Let's get warmed up a little bit.
And the treadmill was slanted at different elevations to make him produce the kind of effort he would if he was climbing a steep hill and walking fast, doing a great deal of exercise.
The cooling effect was very comfortable. I don't recall cold spots or hot spots.
The system worked well, and NASA charged Hamilton with building a water-cooled undergarment.
The cool water flowed into the connector and through the tubing to be circulated around the user's body.
There were hundreds of feet of fine tubing running over the entire body. Hamilton's system would become the standard method of keeping astronauts cool in space.
That was very good. When the astronauts leave the LEM for their exploration of the lunar surface, they'll strap on one of the most important parts of the extravehicular mobility unit, the Portable Life Support System, or PLSS. To learn about this unusual backpack, we visited the Hamilton Standard Division of United Aircraft in Windsor Locks, Connecticut, where the PLSS is manufactured. We talked with Mr. Ronald Lang, project manager for systems engineering.
Here in our space lab, I'd like to show you a full-scale mock-up of our portable life support system, or backpack. This, when used in conjunction with a pressure garment or spacesuit, gives a man all the required essentials for life support. As a matter of fact, it has everything that a spacecraft would have, with the exception of a propulsion system.
You don't have any rockets?
No, we use our legs for the propulsion. When a man wants to put this on in the vehicle, he disconnects the oxygen supply that goes to the suit, that's going and coming from the suit. He disconnects the water that goes to the liquid-cooled garment and back, and this is an emergency oxygen system that goes into the helmet, and then an electrical umbilical. And then to put on this backpack, he faces it in this fashion, turns around with the pressure suit on, and then connects these all to the proper connectors on the suit.
And this just has a harness that fits over his shoulders?
It just puts on a harness. It weighs about 65 Earth pounds.
That's pretty heavy.
But on the moon, it's only about 11, 12 pounds.
All right, because of the reduced gravity.
Right. Now, as a life support system, it contains all the basic ingredients for life support. Chief among these would be the supply and regulation of high-pressure oxygen to the suit. This oxygen bottle sitting right here contains a little bit over 1 pound of oxygen. It's at 850 psi, and it's regulated down to suit pressure of about 1/4 of what the pressure is in this room.
Would that be a little uncomfortable?
No, it wouldn't be, because it's pure oxygen, and as far as a man is concerned, his lungs see the same amount of oxygen as they do on Earth.
See.
Now, as the oxygen goes to the pressure suit and picks up carbon dioxide, it brings it back through these umbilicals to the backpack, and a backpack must remove that carbon dioxide. Otherwise, it'd be lethal to the man.
Really?
What we have to do then is use a chemical absorption bed. We have a contaminant removal cartridge that removes odors and carbon dioxide. Best to show you then a cartridge which is replaceable. We use one of these with each mission. It contains lithium hydroxide and activated charcoal, and it's completely consumed at the end of a mission.
Looks sort of like an oil filter.
Yes, it is. And incidentally, it gives off heat during this process. It adds heat to the system. And I should add that for that to be effective, the fact that it's sitting here by itself doesn't do us any good. We have to come up with a technique for getting the CO2-laden oxygen from the helmet to the backpack.
Right.
And for this reason, we use a fan. And the fan is this gadget right over here.
Oh, I see.
That is a fan, and the fan is powered by an electric motor. We also use a pump to push the liquid cooling, the water, to the liquid cooling garment and back. The pump sits right at this point, and it is also powered by an electric motor.
Well, that's right. To send the water over there and bring it back. And how do you cool the water once it's inside the backpack?
The water has picked up about 8 degrees when it goes through the liquid garment, and the oxygen is coming out at body temperature, and it has a lot of moisture in it. And this is all cooled in this box right here, which is a sublimator. Now, a sublimator is best described by referring back to the big snowbanks in Maine that seem to disappear even though the temperature never goes above 32 degrees. What happens here is that the snow goes directly from the ice phase to the gas phase, and it never melts in between. So the principle of operation here is exactly the same. What we do then is and let me show you, by the way, this is a sublimator, a complete and actual sublimator. The oxygen from the suit comes in through here and leaves here. The water comes in from here and leaves here. The water that we are turning into ice to sublime is coming in from here to here from a reservoir. And what it does is it becomes an ice layer in the layers in here, becomes ice, and to enable it to go from ice to gas, it must pull heat away from its surroundings. It cools this whole assembly down to almost 32 degrees. In fact, the ice is at 32 degrees. And in so doing, the oxygen and the water that go through here are cooled down to the levels that we have to have.
That is very interesting.
Well, we have other things that are in this backpack that are not life support elements per se. Chief among these are communication. We have a communication subsystem which sits right on top of the sublimator and is cooled by it. This is the antenna, and this is the connection here.
So that he can talk back to the LEM?
Exactly. He could talk back to the LEM, or he could talk to the Earth via the LEM.
A little radio station.
That is a complete transmitter and receiver. I'd like to show you a component there. This is the communication system.
It is really small, isn't it?
It's very small and very compact. And it has, in addition to voice, it has 7 channels of information that are continuously telemetered. If the man so desires, he can shut off the telemetry. It monitors the performance and gives us an EKG, electrocardiogram.
Now, just thinking that all these things seem to run on electricity, how do you power all of this for 4 hours?
Well, we power the electric motors and the communication system with a battery, a silver zinc battery, which is also a one-shot deal. We have as many batteries. The battery goes right in here at this point. And there are as many batteries as we're going to run missions. It's 5 pounds, and it's designed with the launch vibrations in the vehicle from Cape Kennedy in mind. It's a very rugged, reliable battery.
And that's enough to run this for 4 hours?
It's enough to run this for 4 hours. Yes, it is. The other thing that I'd like to mention is failure detection. For us to be able to run a successful mission, we must feel confident that we could bring the man back in the event of a failure. And the astronaut will have on here various systems to tell him that he's got problems, if he in fact does. 2 of these will be a low-pressure warning device, which will trigger an audible warning buzzer if the suit pressure goes below 3.2 psi.
How would that happen?
If we had a leak in the system, or if for some reason we stopped supplying oxygen, the pressure would begin to decay. The other thing that we would like to tell him about is if we're using up too much oxygen. We have a flow warning buzzer that tells him, you're using your oxygen too fast. Do something.
Well, if he does get into one of these serious problems, how's he going to get back when he's wandering around in the moon?
He has an emergency mode of operation. He immediately cuts in his emergency oxygen system, which is built onto here for expressly that purpose. The emergency oxygen system is a toroidal, 7,500 pound per square inch supply that contains only 0.2 of a pound of oxygen. And when used in conjunction with the main supply, can give us emergency ventilation and purging of the helmet area, even though the fan fails. Now that thing will go in this area up against the backpack. Another emergency system is the communication. We have a redundant communication system.
But the ultimate and most dangerous test was a huge, specially constructed vacuum chamber.
They were able to pull all the air out, create a big vacuum, just like it would be on the moon. That way we could test our suits to make sure there was no leakage.
One such test narrowly avoided disaster. Jim LeBlanc was the test subject in the vacuum chamber. Cliff Hess, the supervising engineer outside.
Jim, while you're exercising, I'd like you to stay intermediate all the time, okay? I'm pretty cool right now. Okay, well, you'll warm up here in a minute, so let's stay right here if you can stand it.
The testing started just normally, like they all do. And Jim was at a vacuum in the spacesuit.
Well, I feel pretty good here.
With all the air sucked out, all that protected him was his pressurized suit. Then something happened.
I heard over the headset that he was losing suit pressure.
The tube pressurizing his suit had become disconnected. He was in serious danger.
There really wasn't any feeling. It was just happening so fast, trying to get the chamber back to a safe pressure and Jim to a safe pressure. He was inside the suit.
As I stumbled backwards, I could feel the saliva on my tongue starting to bubble just before I went unconscious. And that's kind of the last thing I remember.
Essentially, he had no pressure on the outside of his body, and that's a very unusual case to get, and there's very little in the medical literature as to what happens when you have that. There's a lot of conjecture, that your fluids will boil.
Within 25 seconds, a co-worker, sitting in a partially pressurized antechamber and wearing an oxygen mask, was able to dash in. At the normal rate of repressurization, it would have taken 30 minutes to make the chamber safe. Hess repressurized it in just over a minute.
That's much, much faster than you would ever come down in an airplane. It would really hurt your ears if you did that.
Finally, it was safe to let a doctor in. Miraculously, LeBlanc had already regained consciousness.
When I stood up in the chamber, I felt fine. My ears ached a little bit from the course of rapid repressurization, and that's basically the only effect I had.
It was one of the few instances where anybody was ever exposed to that low of a pressure and lived to tell about it with no obvious damage.
Such an accident in space would have been fatal. But thanks to testing like this, no astronaut has ever had to face a similar situation. The suits were holding up to everything that could be thrown at them, and the program was back on schedule.